And I think also it's great that you've seen the Professor Yang Qiang's talk earlier. So my talk will actually, from the discussion, my talk actually will cover some of the questions that also people asked during the discussion. So I think it'll be a fun discussion. Okay, so let me get started. So today I'll talk about towards building a responsible data economy. As we all know, data is a key driver for modern economy and also is the lifeblood of AI and machine learning. However, a lot of this data, as we know, is also very sensitive. And also like every day we are collecting more and more data, and also there has been estimated that a significant percentage of EU's GDP actually now comes from value from personalized data. And the global economy is at the $1 trillion level, and it's growing rapidly. And as I mentioned, a lot of this data is sensitive data, and we have seen unprecedented challenges in how sensitive data is being used for both actually individuals and businesses. So on the individual side, individuals have lost control over how their data is used. Often users' data actually has been sold or misused without the users' knowledge or awareness, including, for example, even California DMV has been selling drivers' personal information, for example. And a lot of this data has been sold under the premise that the data has been anonymized. But however, a lot of research has shown that anonymization is insufficient in protecting users' privacy. And what's shown here is just an example of a case study that's done by New York Times. They show that from anonymized mobile phone location data sets that they were able to obtain and just from the data market, they were able to track the location of a Secret Service agent with the former President Trump. And hence, you actually get to know the location and the trajectory of the former President Trump. So this is a great example showing that anonymization is insufficient in protecting users' privacy. On the business side, businesses continue to suffer from large-scale data breaches. We continue to see, even for Fortune 500 companies and so on, they suffer from attacks where attackers actually have stolen sensitive information about of like hundreds of millions of users or in certain cases even billions of users. And also privacy regulations such as CCP or GDPR, it's a good first step, but at the same time, they are also becoming a burden for businesses. It's becoming more and more cumbersome and costly for businesses to comply. And more importantly, a lot of the valuable data is actually being siloed and now being utilized due to privacy concerns. So overall, we are seeing tremendous challenges as we move forward in the digital age. And these challenges will only become more and more severe if they are not addressed, to the extent that they could be hindering societal progress and even undermining human values and fundamental rights. And hence, we have an urgent need for a framework for what I call a responsible data economy. So what do I mean by a responsible data economy? Here I list several goals and principles of a responsible data economy. First, we need to establish and enforce data rights. Data rights form the foundation of a data economy and can help prevent misuse or abuse of data. And we need to enable fair distribution of value created from data. For example, users should be able to gain benefit from their data. And ultimately, we want to enable efficient data use to maximize social welfare and economic efficiency, so that data can be utilized for the benefits of individuals, organizations, governments, and societies. However, there are a number of unique challenges posed by some unique nature of data. So first, there is natural tension between utility and privacy. On one hand, we want to achieve the best utility to extract value out of data. But on the other hand, we want to protect individuals' data privacy and so on. And hence, there is a natural tension between the two. And also, data has some very unique properties that's different from traditional like physical objects. One, data has a property called non-rivalry. So for example, if I hold a phone in my hands, then nobody else can have the same phone, hold the same phone at the same time. And this is called rivalry. But however, for data, I can have a piece of data and somebody else can hold a copy of the same piece of data. And then in this case, they can just use the data as well as I can. And hence, this is called non-rivalry. So data is non-rival. And as a consequence, once data is given out, once it's copied, then one cannot really take it back or undo it. And hence, it's particularly challenging to protect data, given the data's non-rivalry property. And also, data has what's called data dependency and data externality. For example, processed data can reveal information about the original data because it's computed from the original data after all. And also data about the one entity oftentimes can reveal information about another entity. And genomic data is a very good example. And because of these unique properties of data, and hence we cannot simply copy concepts and methods in the analog world to address these challenges in the digital world. And hence, we need to develop a new framework for a responsible data economy. And this requires a combination of technical and non-technical solutions. In particular, in this framework for a responsible data economy, we need three components. One is the technical solutions to provide the technical framework to support the responsible data economy. And also, we want to develop new incentive models to better distribute value created from data. And we need the legal framework to support this as well. So now let me, in this talk, let me just talk a little bit about each one separately. So first, let's look at the technical solutions. So first, let's look at why traditional solutions are insufficient. So in traditional solutions, data is only encrypted at rest or in transit. And hence data encryption only protects data at rest or in transit. And also data in this case is when it's being used. So either it's not used or if it's used, it's usually copied. And as I already mentioned before, once the data is copied, then it's almost impossible to control the further usage of the copy data. And further, as I mentioned, anonymization is not sufficient for protecting data privacy. And hence, we need to develop new technologies, in particular, to provide data protection when data is in use. So this has two parts to it. One is that we need to be able to control use of data without copying the raw data. So basically, we need to enable essentially secure computation so that one can compute over the data without actually ever getting a raw copy of the data. And second, we want to protect the computation process, the computation output from leaking sensitive information. To address these challenges, we need to develop different solutions. So overall, I call these responsible data technologies. And because we need to provide solutions for in these different aspects, we actually need to develop different types of component technologies. So here I listed 4 examples of component technologies, including secure computing, which helps protect the computation process from leaking sensitive information, and differential privacy, which can help ensure the computation output doesn't leak sensitive information about individuals. And the and factory learning, Professor Yang Qiang earlier has talked a lot about this, so I won't go into the details. At high level, factory learning can help data to remain at the data owner's device and do distributed analytics and model training to essentially to build machine learning models and so on. And finally, distributed ledger can help provide a mutable log to ensure that data usage is compliant. So now let me talk about some of these component technologies in a little bit more detail. So for secure computing, again, the goal of secure computing is to protect the computation process from leaking sensitive information. And there are two main types of secure computation technologies. One is using cryptographic-based methods, such as secure multi-party computation, zero-knowledge proofs, and homomorphic encryption, and so on. And these type of techniques, in general, the challenge is that they often have high performance overhead, and hence, in general, they can only be utilized for certain specific type of computation. So in recent years, we have seen a lot of advancements in this domain, where, for example, different improvements have been proposed for improving the performance for homomorphic encryption methods and also MPC, secure multi-party computation methods for machine learning, both inference and training and so on. But today, in general, we network inference has improved by 2 orders of magnitude, but still today for it's still too slow essentially for doing even very small network training that would take many days, or in certain cases can even take years. And similarly, for MPC methods, it can be depending on the security setting, it can be faster, but still for larger scale neural networks, for training, it will still take essentially many years to do. For example, for ImageNet, VGG16, and so on. So for these methods, again, they can be utilized for certain smaller computation workloads, but for larger scale computation, it's still there's still a big gap that needs further improvement. So the other type of secure computing technology is based on secure hardware. So the advantage of this approach is that the performance overhead is very low, oftentimes close to native performance overhead, and hence it can also support for general purpose computation. So with the secure hardware, the goal is, in this case, is with the combination of hardware and software mechanisms, it provides an isolated execution environment called a secure enclave. And when programs are run inside the secure enclave, the outside operating system and applications will now be able to see what's running inside, and also will now be able to modify what's running inside, and hence provides integrity and confidentiality for the data and the program execution inside the secure enclave. And also it enables a capability called a remote attestation to enable the a remote attacker from a remote verifier to be able to verify what's running inside the secure enclave and also its initial state, and hence provide remote verification for the correctness of the computation results, as well as the security protection for the computation running inside the secure enclave. So secure enclave, given its strong security capabilities, can serve as a cornerstone security primitive and can provide a platform for building new security applications that couldn't be built otherwise for the same practical performance. Given its importance, different hardware manufacturers have all been developing different solutions for secure hardware. And a number of these actually have now been deployed in the cloud. However, these are all closed source solutions. And to actually, to really enable a truly trustworthy secure enclave, we need to enable open source solution. So at Berkeley, we have been developing a project called Keystone, which is the first open source framework for developing secure enclaves, or TE's trusted execution environments. Keystone is built on top of RISC-V, which is an open source RISC architecture that uses a simple provides simple abstraction and modular and flexible design, and hence can enable minimum trusted computing base, so that it can make it more amenable for formal verification as well. And from our experimental results, it also shows that, for example, on standard machine learning benchmark, the performance overhead is very low. It's essentially close to native performance. And you can try out Keystone today on the latest RISC-V boards, as well as in emulation and also with FPGA and so on. And the Keystone project now is supported by the Global Confidential Computing Consortium for enabling secure computing. So again, today, we still see gaps and open challenges for making secure computing really practical. But however, I do strongly believe that in 10 years, secure computing will become commonplace. In 10 years, most chips will have secure enclaves capabilities. And in 10 years, most computation will use secure enclaves. And also in 10 years, I think we'll see more hardware accelerators for cryptographic methods for secure computing as well, such as for homomorphic encryption. So that's the first component technology, secure computing. Let me quickly talk about the next one, differential privacy. The goal of differential privacy is to ensure that computation output won't leak sensitive information about individuals. So first, let's look at why this problem is important. So one question is that we have been studying is, as we know, neural networks have very high capacity. So the question is, do neural networks actually remember training data? And if yes, can attackers actually exploit this to extract the secrets in the training data from simply querying the learned models? So in our work in collaboration with the researchers from Google and other places, we set out to explore this question. So in particular, we explored in the domain of language models. So with the language models, we train machine learning deep learning model using a text corpus. And so when given a sequence of words or characters, the model will give the next word or character. So here's an example of one of our case studies. In this case study, we show that we trained a language model on the email dataset called the Enron email dataset, which naturally contained actual users' credit card and social security numbers. And our work showed that by devising new attacks, an attacker can actually automatically extract the original users' credit card and social security numbers embedded in the original training data set. This illustrates that even as we train machine learning models, it's important to protect users' data privacy. And in this work, we also propose a new measure called exposure to measure the degree of memory memorization. And this has been used in Google products such as Google Smart Compose. And in our most recent work, we further extended this direction. In particular, we looked at this question, whether this a similar phenomenon appears in large-scale language models as well. So in particular, in this case study, we studied the language model GPT-2, which is one of the largest language models. And our work shows similarly that by just querying the GPT-2 model, we were able to extract personally identifiable information that has been essentially remembered by the GPT-2 from the original training data set. So, right, these examples illustrating that it's important to protect, to take essentially measures to protect users' data privacy as we train machine learning models. So what can we do? So one method is that we can utilize differential privacy. So instead of training a vanilla language model, we can train a differentially private language model instead. And in our work, we show that for certain tasks and for certain use cases, for example, for training language model of a certain scale, our work showed that by training a differentially private language model in this case, it actually can still achieve similar utility, but at the same time, it can significantly enhance the privacy protection for the language model. But however, of course, it's still an open challenge for really large scale language models. Training differentially private language model with similar utility and also in an efficient manner is still an open challenge. And right, so really depends on the specific use cases. And also in our recent work, we have also developed new techniques to make it easier to deploy differential privacy mechanisms. For example, we've developed methods to automatically rewrite data analytics queries to embed differential privacy mechanisms into the queries so that the analyst doesn't need to know anything about differential privacy. And the rewritten query will automatically satisfy the differential privacy, and the results will automatically be differentially private, and hence make it much easier to deploy differential privacy. And also in our recent work, we have developed new higher order language and linear type system for statically enforcing differential privacy and provide automatic proofs that, for example, a machine learning algorithm is differentially private. And our work to it won the Distinguished Paper Award at the top programming language conference. And the technologies that we have developed also have been piloted and used in different real-world settings. So due to time limit, I won't go into details for some of these other components. And overall, when we combine these together, we can enable a platform for a responsible data economy by building a secure distributed computing fabric. And the vision is that by utilizing this platform for a responsible data economy, we can also enable new a new paradigm for more effectively utilizing data. In particular, we can enable what we call data commons for essentially decentralized data science. So in this case, we can have different data owners and data producers from different data sources, and they can register their data sets with different policies specified how they want their data set to be utilized. And this registration can be collected in a distributed data catalog. And the data consumers or data analysts can go through the distributed data catalog to find relevant data and write the data analytics and machine learning programs over these different data sets and data sources. And after essentially ensuring that the program is compliant with the desired policies, then the program can be executed using secure computing techniques to ensure that the result, the computation process is secure, and also in the end, the results satisfies the desired policies from the data owners and producers. So overall, this approach can reduce friction of data usage and remove data silos and enforce strong security and privacy protection. And I believe that in 10 years, data trust and data commons will become predominant ways of utilizing diverse sources of data and enabling ownership economy where users benefit from their data as owners and partners. And also in 10 years, we'll see data stewards, fiduciaries, and trustees emerge as a new class of entities important in the data ecosystem, helping manage and protect users' data and grow its value. And in 10 years, huge economic value will be created through these new forms of data trust and data commons, orders of magnitude higher than today's data marketplace. And also, I'm also the founder of a startup called Oasis Labs, where we are actually developing some of these technologies. And by combining in particular, by combining privacy computing and blockchain, we can create a new type of asset that we call data assets. And in this case, blockchain allows for essentially for establishing this immutable ledger of users' rights to data and the policies of how they want their data to be utilized. And privacy computing ensures that data remains private during compute and cannot be reused without permission. So the capsule of data and policies creates an assets that can be consumed along the specific guidelines and enable exchange of value. So with data assetization, we hope to help unlock a new responsible data economy where users and businesses can maintain data rights and earn value from their data assets. And in particular, our technology has been applied in the domain of genomic data, where, as we all know, privacy is really important. And in this case, using the technology, we help users to become owners of their genomic data. And at the same time, they can maintain control of their genomic data and also enable their data to be utilized in a privacy-preserving way. So far, I've talked about the technical solution component for the framework for a responsible data economy. Let me also just very briefly talk about some of the other components just very quickly. So one, I wanted to briefly mention the second component for incentive models. So essentially, we need better incentive models. In particular, how can we determine and distribute value of data? So in our recent work, we show that we can model machine learning as a collisional game, where the data distributors are players in a collision, and the usefulness of data is characterized by a utility function. And in this case, our work showed that a concept called Shapley value actually provides the only and unique solution for distributing values to the data contributors of a machine learning model that satisfies a collection of desirable properties. And Shapley value, the original concept, was proposed by Alois Shapley who is a Nobel Prize laureate in economics. And also our work showed that Shapley value can also provide as a good measure of importance of data points. And also our work proposed various techniques how to compute the Shapley value in an efficient way as well. And finally, I also wanted to briefly touch on the question of legal frameworks. So essentially, in the data domain, we still have many open challenges. For example, what are data rights? Who controls data rights? For example, individual property rights have been a cornerstone of modern economy, and the establishment and enforcement of individual property rights has helped establish modern economics and fueled centuries of significant growth. However, in the data domain, we lack an adequate framework for data rights. Establishing data rights will allow individuals to derive value from their data and propel economic growth and unlock new values. And there has been a broad spectrum of different concepts and frameworks proposed in this area, and it's an exciting open area for exploration as well. And overall, we need data-driven, technology-informed regulation. So in China, for example, the various different government agencies, entities are looking at how to establish better regulation for data privacy, data usage, and so on. But the question is, how will advancement of responsible data technology influence and impact regulatory frameworks? And how can regulation help with faster, broader adoption of responsible data technology? So overall, I hope from my presentation that you have seen that for the future of the internet, we must build a responsible data economy. And I think the decade of 2020 is an important time, and also is a great time for moving ahead on this. And the decade of 2020 is, I believe, the decade for building a responsible data economy. Thank you.